Hello and welcome to our project. This is the first grade STEM fair. This is Miss Wayman's class, and we're hungry, okay? And we want to cook a pizza, all right? We want to cook a pizza in a specific way by using the sun's energy to do so. Now, we could set the pizza outside. However, for a pizza that needs to be cooked at 425 degrees Fahrenheit, it could take quite a while to cook. Probably won't taste as good, especially now being, I guess, the winter down here in Apollo Beach, and still 70s. I don't think will get the job done. However, we could use solar panels to produce electricity for the oven to cook the pizza at 425 degrees. But the problem is, if we're wanting to cook and eat this pizza in the classroom, carrying enough solar panels to power the oven along with the inverter to do so would be quite exhausting and a daunting task. So we could use a battery to store the sun's energy, and that portable battery could be brought to the classroom to then power the oven to cook the pizza. And that's what we're going to do. Before we begin, we need to have a better understanding of how electricity works. To keep electricity terms short and to the point and not confusing, let's talk about the three big factors. Those three big factors with powering electrical appliances will be amperage, or amps for short, voltage, or volts for short, or wattage, watts for short. If you think about electricity, specifically electricity in your home, think of it in terms as water flowing through a garden hose into your home. In your home's breaker panel, let's take for example two of the most common circuits, a 15 amp and a 20 amp circuit. Basically, a 15 amp circuit is a garden hose allowing electricity to flow into the connected wall outlets that you plug your electronics into. However, a 20 amp circuit is an even bigger, wider garden hose that allows more electricity to flow to those outlets. And the volts will be the intensity, basically how fast that electricity is flowing to those wall outlets. In our experiment, we'll be using the standard outlet found in your home, which is a 120 volt outlet. Taking what we learned about amps and volts, let's take a bigger appliance in the house, say a 240 volt clothes dryer that will dry your wet clothes. This appliance is going to consume a lot of energy, which is going to take a higher rated circuit. For example, a 30 amp circuit, which is even bigger, wider garden hose that allows 240 volts, so a lot of electricity, very fast, going into that dryer. Usually this 30 amp circuit is wired by combining 220 volt wires into that circuit for even more faster and abundant flow of electricity. As the dryer consumes the electricity, it does so in watts. A 240 volt dryer can use anywhere up to 5,000 watts of energy, which is a lot. If you look at your electric bill, you will see you get charged by the kilowatt hour. So say we were running a dryer that consumes 5,000 watts for an hour. Since 5,000 watts is 5 kilowatts, you'll be charged for 5 kilowatt hours of energy used. Now with that understanding about electricity out of the way, let's talk about the battery. Now the battery we're going to use is a fully charged EcoFlow Delta Pro battery, which is going to give us enough output for the power we'll need for the oven, which can consume roughly about 1.7 kilowatts of energy when heating. In order for the battery to output that energy, it needs to be stored first, then discharged via chemical reaction. Regarding batteries, you will hear the term battery chemistry, or battery chem for short. Whether we're talking about lead acid batteries or one of the more rapidly growing popular batteries today that is very energy dense, and that's why you see it in portable devices, say phone, tablets, laptops, or even cars, is the lithium ion battery, which is what the EcoFlow Delta Pro uses. Now recently there has been awareness raised about batteries using cobalt. I won't expand on that in this video, but I will highly encourage everyone to research batteries that contain cobalt, where it comes from, who it comes from, and why shopping for batteries without cobalt is a good thing. Fortunately for our experiment, the EcoFlow Delta Pro battery chemistry is lithium iron phosphate, which is a more abundant, non-toxic resource that comes from a more reliable supply chain. Batteries have two electrodes, an anode positive on one side and a cathode negative on the other, with an electrolyte separator in between. The electrodes work together to initiate a chemical reaction that releases electrons. The electrolyte, usually a liquid, makes it possible for the resultant electrical charge to flow between the two. And this is what produces electricity. As we trace back the path of how the battery was charged with the sun's energy, we come to the topic of solar panels. These panels capture the sun's radiation and turn it into electricity, a process known as photovoltaics. This process generates voltage or electric current in a photovoltaic cell when it's exposed to sunlight. Although it's a complex topic, to keep everything brief and as easy to understand as possible, the sunlight is composed of photons, which are simply small bundles of electromagnetic radiation or energy. Energy from the photon is transferred to an electron of the solar panel's semiconductor material, causing it to jump to a higher energy state known as the conduction band. In their excited state in the conduction band, these electrons are free to move through the material, and this motion of the electron that creates the electric current in the cell. Now that we have the science explanations out of the way, let's hear from the students and what they have to say prior to the experiment.
The sun and the solar panels will stay the same during the experiment.
Our materials are a pizza, batteries, oven, blocks, and solar panels.
My hypothesis is we can cook a pizza with solar energy.
We are going to be measuring our data with blocks.
And use solar energy to cook pizza.
We are changing the angle of the solar panel on the sun. Baking pizza with solar energy.
Alright, now on to the experiment. So basically, as you can see here, we got a solar panel on the ground and the batteries in the garage. So we introduced many types of variables in this situation because through the app that comes with this battery, we can monitor the input. Now this panel is rated at 400 watts. That means the max that it can input into this battery is 400 watts. So we see by laying it on the ground, we're getting an input rating of 266 watts. Now let's change some things up a bit so that we can see if we could change the output of the panel and the input to the battery. As we saw previously with the panel completely exposed, we had 266 watts of output. Now covering up half of the panel, we can see that we've halved the input to the battery, so we're getting an output of about 126 watts. Let's change some things up a little more by angling the panel more directly towards the sunlight. And what do we get? We're almost getting the full output of the panel at 360 watts. Again, covering half of the panel, we can see that it decreases the output of the panel. Next, to make things even more interesting, we brought another solar panel into the mix. Now, just like batteries, solar panels produce DC or direct current, and with that you can do the same experiments that you do with batteries by stacking up these panels in series. So by connecting a positive and a negative cable coming out of the panel and then taking the remainder positive and negative cables, we then pipe that into the battery, and we have now not only added the capacity of the 400 watt panel output, but the capacity of the 200 watt panel there laying on the ground. Now, after all that sunlight was soaked up by the panels and input to that battery with a fully charged battery, let's see what we can do with it. After a nice trip to the school, we wheeled this battery in, and we also brought in our oven. And so we had a few pizzas we had to cook, and so we then plugged that oven into the battery, and it was thirsty. It was taking about 1.7 kilowatts of energy, but we were able to get that oven up to 425 degrees and cook these delicious pizzas. Let's see all of our young scientists or students' reaction. So it looks like everyone enjoyed the experiment. We learned a lot, and I hope you did too. Thank you for watching, and we'll see you at the next STEM fair.